So let's start and let's meet. Who am I? I'm Aliaksandr Valialkin, and you can find me, my posts, my work in internet by googling my nickname Valiala, and I have a GitHub repository with the nickname Valiala. You can scan QR code and go to this repository. Then I have Twitter account, active Twitter account, where I post my thoughts, and also have LinkedIn account where I also post my thoughts. Almost the same information as in Twitter. So I'm fond of creating useful programs which are optimized for high performance and low resource usage. And I write such programs mostly in Go, because Go is a very practical language. It has very concise syntax, and it is easy to write non-trivial programs in Go and still maintainable programs. And I enjoy when users are happy while using my programs I create. And also I'm a CTO at VictoriaMetrics, a company. Have you heard about VictoriaMetrics before? Oh, cool. Okay, let's return to our topic. Who generates the most of the logs in Kubernetes? Probably this is a Kubernetes control plane or API server. I don't think so. And probably that's Kubelet installed on every Kubernetes node. And the answer is no. And the correct answer is the most of the logs are generated by user applications or microservices which are deployed in Kubernetes. And the number of logs is proportional to the number of deployed microservices multiplied by the number of replicas of these microservices, the number of pods. So I personally prefer monoliths, but we are at the stage when the majority of developers prefer microservices, and these microservices are interconnected, and there are also usually a lot of microservices in users' deployments, and they communicate with each other and generate a lot of logs. So I'm the also architect who prefers keeping it simple, but we are in the market when architects prefer adding microservices everywhere and generate a lot of logs per each microservice in order to be able to debug their microservices. So let's do some simple math. According to our statistics, the average log size in Kubernetes is 1.5 kilobytes. And the typical log looks like this one. It contains many fields, small fields, and the most important field is the log message itself. It is not so large compared to the last of fields. The most important field also timestamp, and there are other Kubernetes-specific fields such as container name, pod IP, node name, pod namespace, and pod labels, and probably other labels. But that's the most common labels per each log entry in Kubernetes. These fields are needed for being able to grouping by these fields and filtering by these fields when you investigate these logs. And let's suppose that every pod generates 100 logs per second. And let's suppose that you have 1,000 pods, and then these pods generate 100,000 logs per second. And if you multiply this number by the number of seconds per day, you get 8.6 billion of logs per day, or 13 terabytes of logs per day. And if you multiply this number by the number of days in a year, you get 3.2 trillions of logs and 4.7 petabytes of logs per year. And 4.7 petabytes of logs is quite big number. So how to efficiently store and query such amounts of logs? There are many solutions and databases, and let's look at some of these solutions. How about storing these logs in relational databases such as Postgres or MySQL? I think that you should try it and figure out that it doesn't work because these databases aren't designed for such volumes of logs. And if you will try it, you will get this meme. How about Elasticsearch? Elasticsearch is used by many users, companies for storing logs and querying logs. But did you try storing 4.7 petabytes of logs in Elasticsearch? Yeah, you can try and it will work if you have millions of dollars on infrastructure for running Elasticsearch cluster which can handle such amounts of volumes of logs. Because Elasticsearch requires a lot of memory proportional to the amounts of logs you store in Elasticsearch for being efficient. So in this case, it will require hundreds of terabytes of memory, I suppose. How about cloud services such as Datadog, Splunk, and so on? Yeah, they also work, but at that scale, be prepared to pay tens of millions of dollars per year. And if you have such money, you can use these cloud services and be happy because cloud services are very good. They provide good functionality. But if you have no tens of millions of dollars per year, then that will not work for you. How about Grafana Loki? Yeah, it works, but the downside of Grafana Loki is that it is too complicated for configuration, for running, for troubleshooting. Why? Because it contains many components. For example, this standard scheme of Grafana Loki, which contains 1, 2, 3, 4, 5, 6, around 10 different components, which each component has its own configuration, non-trivial configuration, which is barely documented, and you need to figure out how to configure all these components together and optimize them together. Here is a list of these components from official Grafana documentation with some checkboxes. So it's not trivial. And how about ClickHouse? Yes, ClickHouse is good database and it can deal with big amounts of logs if you know how to properly configure it, how to properly create a database scheme for your particular logs, for your logs with the given set of fields and for your particular queries. If you do not know how to how to create this database scheme or table scheme for ClickHouse for your workload, then it is likely that you will end up with not so fast solution which requires a lot of memory and CPU. And okay, then you can use on-prem solutions on top of ClickHouse, such as ClickStack, Signos, and so on. Yes, you can. These solutions already go with pre-configured table database schemes, which are optimized for typical logs. But the problem is that they are not so trivial to configure on large scale. Why? Because ClickHouse requires it has not so simple configuration, and it also requires Zookeeper or ClickHouse Keeper when you scale it to multiple nodes. And Zookeeper and ClickHouse Keeper are known to be the most annoying part of ClickHouse cluster, which usually have some issues, problems, and bugs. Here an example of bugs from Zookeeper from ClickHouse repository, and here an example of bugs from ClickHouse Keeper, which are still open in ClickHouse. And other than these bugs, you face with other problems which are already documented and not considered as bugs. Okay, and what about VictoriaLogs? Yes, it works, and it works perfectly. And if you know what is VictoriaLogs, I'll talk a bit about it. This open source database for logs. The open source is very important here, so you can use it for free, and all the functionality of VictoriaLogs is available in open source. Almost all functionality, except of some enterprise features. It supports collecting logs from Kubernetes out of the box with a very simple Helm chart. You can scan this QR code and read documentation about this Helm chart and install it in your Kubernetes cluster, and it will instantly start collecting all the logs generated by all the pods inside your cluster and store them in the configured destination, usually this VictoriaLogs. And it collects these logs with a specially written VictoriaLogs collector, which is named VLegend, and this VLegend is very efficient. It is much more efficient compared to other collectors such as Vector, FluentBit, OpenTelemetry collector, and so on. And I recommend you scanning this QR code and reading a blog post about it. This blog post is highly technical, and you can try it, reproduce it, the benchmark inside this blog post, and understand that VLegend is much more efficient compared to the other log collectors for Kubernetes case. And VictoriaLogs works optimally with default configuration. You don't need to configure anything in any environment. It automatically adjusts the configuration and resources usage for the environment where it runs, for the available memory, CPU, disk I/O, and so on. And it is schemaless. This means that you don't need to bother about table scheme, database scheme. Just ingest logs into it, and that's it. And it is optimized for petabytes of logs on a single node setup. You can basically store petabytes of logs. I will show you later about some numbers from real production system. And it can scale to hundreds of petabytes of logs in cluster setup because it's very easy to scale from single node version of VictoriaLogs to cluster version. Just add more nodes. And the number of nodes in the cluster can reach thousands. And this system doesn't need object storage. Probably some of you may think that it's a drawback, but I think that it's an advantage. It stores data on the provided persistent volumes, which it is optimized for both SSD and HDD-based persistent volumes. It saves lifetime for SSD persistent volumes, for example, and it works very fast during querying and during data ingestion even on HDD-based volumes with a small number of available IOPS. And the advantage of storing data on persistent volumes is that they usually have 100 times lower latency for when you access the data. The latency is usually less than 1 millisecond when you access the data on persistent volumes, and the latency for accessing data in object storage is usually up to 100 milliseconds. So it's 100 times bigger. And this affects queries over big amounts of volumes. And VictoriaLogs shards data in per day partitions and stores data for every day in a separate directory. And this simplifies managing and backupping such data to object storage on a per day granularity. And let's look at some real production numbers from VictoriaLogs. We run VictoriaLogs internally for collecting logs from our Kubernetes staging cluster for the last 2.5 years, and we run single node version of VictoriaLogs with the following limits. It has 32 gigabytes of memory, 8 CPU cores, and 1 terabyte HDD-based persistent volume with the limit of 120 megabytes per second of disk read-write bandwidth and 750 IOPS. And we stored 3.7 billion of logs over this 2.5 years in this VictoriaLogs instance. That's not so big number, but it's still big. And the size of these logs, original size of these logs, is 5.5 terabytes. And you can notice that the size of these logs already exceeds the size of disk, 1 terabyte disk. And these 5.5 terabytes of logs are compressed to 67 gigabytes on disk. And the compression ratio is 82 now. And this VictoriaLogs system uses 600 megabytes in steady state when it accepts logs and do not run any big queries. So let's look at some queries over this 3.7 billion of logs. The first query is just counts the number of logs. That's a query. By the way, the query language is used here is LogScale. It's custom query language optimized for querying typical logs. And I guess it's, I hope that it is not so complicated that it's easy to understand. You can see that it's pipe-based. Initially, you specify filters. In this case, you specify filter on time, select all the logs for the last 3 years, and then count the number of logs. And such query is executed in a quarter of a second. And why is it is so fast? Any guesses? Yeah, probably you guess that it maintains the counter of logs inside the database, and the answer is no, it doesn't maintain such counter. Instead, it stores the meta information in block headers, and block header it stores logs in blocks, and every block has block header, and such block header contains the information on the number of stored logs in such block. So in order to execute this query, VictoriaLogs needs just reading the block headers, and the number of such block headers is 3 million in this case. And the total amounts of data which needs to be read during for execution of this query is slightly more than 100 megabytes. And these block headers are stored close to each other on disk, so they can be read in one go in small number of disk read operations. That's why the query is so fast. And let me check my time. Okay. Yeah. Okay. I can show you a live demo for this query and show some details. So here is a query command line interface for querying VictoriaLogs. It is already set up for querying this staging system, and we can execute this query here. Just find it. Where is this query? Oh, this one. So we execute it, and we see the execution time is quarter of a second, and the number of logs is 3.7 billion. here. And if we can execute it again, you see that the number is different because the system continues working and continues accepting new logs. Okay, let's go further. Another example. Let's count these logs and group them by months. And you can use this query. It selects all the logs and then performs stats pipe, which groups logs by months and counts the number of logs and then sorts the results by time. Let's execute this query here. This one. Oh, it's quite long. Oh, it's quite long, and it shows not useful. It is not easy to read the output. Let's switch to compact mode and execute it again. Yeah, this output is easier to read, and you can see that the query took 3.6 seconds, and you can see the number of logs per each month for the whole lifetime of this database. Okay, here duration is 3.3 seconds. Why it's so slow compared to the previous query? Because you need to convert every timestamp to months. And if you divide 3.7 billion of logs by 3.3 seconds, you get that VictoriaLogs, a single node version of VictoriaLogs, performs this conversion from timestamps to months at more than 1 billion timestamps per second. Okay, then the next query is let's count the number of logs with rarely seen word inside these logs. These typical queries when you need to search for logs for some trace ID, for example, or user ID or IP. The query is here. The foobar word is very rare in this database. So let's execute it and see how it goes. So this is a query. Oh, it takes 2.4 seconds. Let's execute it again. Probably it will be faster. Oh, yeah, it is faster at 1.2 seconds. And important point that VictoriaLogs doesn't cache query results. It executes this query again and again every time. So it finds slightly more than 400 logs with foobar word among these logs. Okay, and the duration of the query is 1.2 seconds to 1.4 seconds. And how does it find these logs among 5.5 terabytes of logs? If you divide this number by the query execution time, you get 3.9 terabytes per second. And the answer is simple, is that it uses Bloom filters for finding this message. And the size of Bloom filters in this database currently is 5.4 gigabytes. So it just reads this 5.4 gigabytes. But if you divide this number by the disk read speed for the disk used for VictoriaLogs, you get 45 seconds. And this doesn't match our 1.2 seconds or 1.4 seconds. Why? Because on the first run, VictoriaLogs reads these Bloom filters from disk, and the operating system automatically caches this data in memory. And in this case, the amount of memory is enough for storing these Bloom filters, because we have 32 gigabytes of memory, and the Bloom filter size is 5.4 gigabytes. So subsequent queries read data from auth page cache, not from disk. Transparently read this data from the page cache. And that's why they are so fast. And let's execute a more practical query. Yeah, such as let's count the number of logs for some particular container. This one query. And let's look. Okay, I have not so much time, so let's speed up. If you execute this query, you get around 8 million of matching logs, and the duration of this query is half a second. Why it's so fast? Because this Kubernetes container name field belongs to the log stream field. The log stream is a stream of logs received from a single instance of some application. And every instance of application has its own constant container name. The data for this field is stored in block headers, and the amounts of block headers need to read, which need to be read during the execution of the query, is 1.6 gigabytes. So the query is fast, but it can be speed up if we will use special so-called stream filters. And you can compare this query to this query, and you see this curly braces here, these stream filters. And if you execute the query, you will get the same results, but the query performance will be 10 times faster. Why? Because when you use stream filters, then VictoriaLogs can reduce the number of blocks or block headers to scan. It just scans only blocks for the given log stream filter, and the number of such blocks is significantly lower compared to the total number of blocks, and the amounts of data needs to be scanned for this query is also much smaller. That's why the query is so fast. And the next, let's skip this because I have no time. And what about queries? All the previous queries were running across all the logs stored for the last 3 years. And what about more practical logs when you queries when you select logs for the last week or last day? For example, let's log this query. It selects logs over the last week. It selects 11 million of logs, and the duration is only 2 milliseconds. The filter on timestamp efficiently speeds up the query. The smaller the time range, the faster the query. That's another example with logs with the error words. The query performance is also quite fast, 50 milliseconds for the last week. And there are some performance tips. Let's skip them because I have no time. You can read these performance tips after I will share this talk later. So how much data can be stored on a single node instance? Let's do some extrapolation. So 5.5 terabytes of logs occupies 67 gigabytes of disk. And this means that 1 terabyte of disk can, in theory, can handle 80 terabytes of logs. And in Google Cloud, you can set up persistent volumes with 64 terabytes of memory. And if you multiply these numbers, you get 5 petabytes. So in theory, you can store up to 5 petabytes of logs on a single node. And let's keep this. So VictoriaLogs uses small amounts of memory, contrary to Elasticsearch, and you can add more memory if you want speeding up queries. And as for CPU, you can add more CPU cores in order to speed up query execution. And if you want storing hundreds of petabytes of logs, it's easy. Just switch from single node to cluster version. The cluster version just spreads these logs across all the available storage nodes, and the capacity and performance scales linearly with the number of storage nodes, unless you hit a bottleneck on the network bandwidth. And it can scale to hundreds of nodes. And there are some quotes from our users. The first user switched from Elasticsearch to VictoriaLogs and saved more than 27 times of resources on memory and CPU. And another quote is from the user who switched from Loki to VictoriaLogs and saved a lot too. You can scan this QR code and read more about this. And try VictoriaLogs on a large-scale cluster. That's it.
A big round of applause for these big numbers.